Hi, Craig.
Hello.
Hey, what's up? Good morning or night.
Hello, everyone. Thank you for coming. This is just about everyone who said they were going to be here, I think. Give it a couple more minutes.
What degree is this going to be an extension of the previous game theory talks? Is this a similar thing? I have no idea what a K-rejecting game is, for what it's worth.
Well, this is just going to be an introduction, really. I'm not going to... Reinventing the entire field for this extension would be a lot to ask, I think.
Okay, gotcha. I didn't even know if this was like a combinatorial game theory thing or if this was some kind of other game, some other
It's...
field of game analysis.
But it is like... It's an extension of combinatorial game theory, but it's one in which a lot of the tools you have don't quite apply.
Okay,
You'll see what I mean in a bit.
yeah.
Basically what we're going to see here is that things are messy. So I'm going to make sure everyone's properly equipped. I'm going to give you all instructions to kind of the swamp these games all live in. Show you some cool like bugs and rocks and sticks I've found, and maybe we can roll around and get dirty a little if time permits. That's kind of the plan.
Sweet.
There's no like master result to build up to that I'm going to show off. It's just going to be a little discussion.
Oh, sounds like fun.
All right. Well, it looks like everyone's here. So let's get right into it. This is K-rejecting games. Just to review what a game is, it's a state mutated by players according to rules and conventions of play. What I mean by all this is state is just the description of the game itself, tokens, boards, who all is here, what each player has. Rules dictate how players are allowed to change the game. And these conventions of play I'm talking about are sort of everything else about the game. Sort of the structure under which we are playing all of these games. Okay?
Hmm.
So, to be more specific, in game theory, especially combinatorial game theory, our goal is to understand simple games and then use that knowledge to deduce things about combinations of games. And so, conventions of play are those aspects of games that don't really combine well. They are the rules of the game that can interfere with other games. So some clear examples are... Why isn't my slide advancing? Oh, I'm up there. The win condition. In combinatorial game theory, we have these two methods of play that we often encounter, normal play and misera. And basically what they say is, in the empty position, where no one can do anything, or, well, where you can't do anything, either you've lost normal play or you've won. And so the simplest way to get a contradiction is to say, well, what if we're playing some of each of these at the same time, right? You have no moves, but there are some games saying you lose and some games saying you win, right?
Yeah, I think that makes sense.
Yeah. And so we get this issue where clearly you have to win or lose, but at the same time, all of these games that you're playing at the same time are supposed to be treated equally. You're not really supposed to favor one or the other, or at least if you did, that would skew how you would analyze them. Right?
Yeah.
I'm with you.
Okay. Another way we can get a contradiction is with turn order. Imagine we all sit down and play Uno plus Uno, right? So I deal everyone here a hand of cards for a game of Uno, and then a different hand of cards for a different hand of Uno. And we can imagine everyone going around playing the games in parallel, putting cards on one pile or the other pile, depending on what game you want to play in. But as soon as someone plays a reverse or a skip, suddenly we have an issue because now the two games that we're playing disagree on who is supposed to go next. And again, we can't favor one over the other, even though it might make sense to say, all right, whichever game was played in last dictates who goes next. The two games are still going to disagree on that. So turn order is another convention of play that all the games we play in conjunction with one another have to agree on.
I have a question about the sum of games concept. If
Yes.
that's okay.
Go ahead.
So, you were talking about this win condition thing.
Yes.
When we say we have a sum of games, presumably they each have an individual win condition. What is the normal way to have the sum win condition? Like, is it that you win any of the games, or do you have to win all of the games, or is it something else?
My understanding is usually once all the games have concluded, or at least you can't move in any of them, so they're all over for you, then the
I
game is
see.
over.
So it's
Yeah,
not
so I think
actually. Go ahead.
Deer can correct me if I'm wrong on this, but like under the normal play condition, I think in the sum, you win if you make the last move in any game, and in the misere condition, you lose if you make the last move in any game.
So it's. So if I lose when I have no available moves, I lose if I pick a game that has no available moves, even if I could have picked some other game that did have available moves.
Sorry, I think I said that. I think I worded that very poorly. The final game. So like these
Okay.
games, you end up uh sort of killing off games one by one, basically. Like they end up each collapsing to like not being any moves left.
Right.
So like under the sum normal play condition, like you at the very end where there's um like no games left and you have no move available, that's when you lose.
Got it. So it's not
In the misere
actually.
condition,
It's the
yep,
reverse, yeah. So it's not.
yeah,
So I should not think of individual game of me winning or losing individual games ever. It's just the whole game, each of which consists of things that I can play moves in, and then there's a universal win condition, which is like the lack of moves.
Correct.
Herb can
And
correct me
all
if
of
I'm
the
wrong,
sub
but I
games
think
need
that's
to agree on that.
Right.
yeah.
Because it's not really a property of the subgames in the first place. It's a property of the sum as a whole, which is just what you're saying, I think. But yeah, thanks
Yeah.
for clarifying.
Were we not going to start considering cases where they don't agree? I was assuming that.
Maybe we were going to consider that, but previously, at least, I don't know. Sorry.
Yeah.
I'm a little confused about this Uno thing. Like, because the turn order isn't preserved in the first place. Like, I could play game one and then player two could play game two. And so from game one's perspective, we skipped them. So why does it matter if the skip card skips them in general?
I mean, that's fair. Maybe that wasn't the best example. But I just wanted to say, like, turn order is another thing that games can disagree on.
Okay. Just
I
an
think
example of we
Yeah,
want
I
to
wasn't
try to apply things fairly
right.
across.
This
Okay.
is
got it.
just setting the stage for me talking about K rejection, which is going to come up on my next click here.
Okay.
So I wasn't
cool.
going to make like
Well,
this big theatrical example for it.
yeah, I guess I think the worldview from which this description makes sense with Uno is like each game has an influence on the player whose turn it is, and like um so the turn order can vary between games, but each game sort of has each game wants the turn order to follow the same procedure. So like if one game hears that a skip was played and the other game didn't hear that, and they both have different mindsets of whose turn should be next.
Right, because if we talk about normally like simpler games being played in succession, hang on, where am I going with this?
Yeah, like with the simple games, you'll still have the same problem. Like even if we're talking about like domineering from yesterday, like in the case of domineering, you have uh like each game still wants players to make consecutive turns, like player one, then player two, then player three, or player one, then player two, then player one, then player two, and so on. But like there's no issue raised there with the turn order swapping or two players going in the same game twice in a row because the other player went in a different game.
Yeah, because in a normal like combinatorial combination, one of the players can make a move in one game several times in a row from that game's perspective. So that would a more general version of that is kind of the case I'm considering.
Okay.
But anyway, I said all that to say that K rejection, what we're going to talk about, is another one of these conventions of play. More specifically, it is an infinite family of conventions of play indexed by natural numbers. So we're going to be talking about 1 rejecting, 2 rejecting, 3 rejecting. We can also have 0 rejecting, which is back to how combinatorial games are typically played, with people just taking turns and no additional complications being introduced. So under each of okay, so under each of these conventions, for some fixed k, there is a structure on each player's turn. The player to move declares intent to make a move. So let me see if I can switch my. It's gonna let me switch my scene here. 1 second. Okay, can everyone see that?
Circles on a grid?
Yes. So let's say we're playing a game with these 2 piles of tokens here. Alice can say, I want to get rid of these 2 tokens. She declares intent to make a move. The move hasn't happened yet. She says, I want to make this move.
Sorry, is the game here like Nim or something?
Nim is one of many games that you can play under this.
Okay.
Why
I don't know what the moves are here in this game with circles on a grid, but
yeah, well,
maybe
I'm
it
going to
doesn't
be
matter.
analyzing a lot of Nim, so let's just get this straight. We're playing Nim here.
Okay.
The reason I made sure to say that K rejection is a convention of play is because this is something that exists sort of independently of a lot of the other properties of games that we study. You can have K rejecting chess or Risk, or it's independent of like being partial or impartial, or 2-player or 3-player, or normal
Okay.
play or misera, or any of the other various conditions we can impose on games. But I'm just studying Nim to keep things simple because this is an introduction.
Cool.
So Alice wants to take that pile, right? Bob can say, no, you don't get to take that pile. he has K choices. K opportunities to reject a move that Alice intends to make. But he can't reject Alice's last available move. She always has to have an option. And then if he rejects her move, she picks a different one. So if he rejected this move, she can say, oh, well, maybe I'll just take this one token. Or she can take the other pile. That is a different move. Bob has not rejected it. She can play it. The components exist independently of each other, just like in standard combinatorial games. K rejections per turn. So suppose she takes that pile. How do I go back? Once she takes that pile, now it's Bob's turn. Bob can say, oh, I'm going to take the whole pile and make you lose. And then Alice can say, no, you can't do that. And then Bob just has to take the one token. Does that make sense?
You want to try a game?
Seems good. I buy it.
Would you like to try a one rejection nim on those two piles?
Sure, we can play that. Actually, the game on the right, I was planning to play with you guys.
Okay.
After I went into a bit of how analysis works. We can start with 2+2 just as an introduction. If all of you are interested. Let me set that back up quick.
Great, yeah.
Okay.
Dirb asks, is it up to K rejections per turn or up to K for the whole game? I think the answer is K per turn, right?
Yeah, each
Yeah, I
turn.
think we're at some point.
Yeah.
Oh, gotcha. Sorry. Yeah, I wasn't paying attention to the chat.
Yeah, I saw he asked that, so I tried to clarify that each turn goes through K loops of this make a decision. Yeah, thank you for putting that in the chat. All right.
We're playing normal or misère for our example game.
Let's play normal.
Okay, who's playing? I'd be down to play.
I will let you guys go first.
Someone else. Oh, are we collectively playing against you?
If you like.
All right. Anybody have any strong opinions? Are we going first?
Yeah, go ahead.
Yeah, the person said to go first. Yeah.
Okay.
Oh, sorry, we're playing one rejection, normal play.
One rejection, normal play. Correct.
Okay, so I mean,
to keep things simple,
we can make any move we want because there are two possible copies of every move. So if they reject the first one, we'll just make the other one.
Yep.
So just remove one from a pile.
Yeah.
Isn't remove two winning? Because then they have a stack of 2, and we can reject them removing the whole pile and leaving us with the loss. So then they will have to remove 1.
I think that works out.
I think remove 1 might also be winning, but importantly, remove 2 is
I think it's winning
definitely
under both options. Maybe not.
Yeah, I'm not sure.
Remove
but
2
sure
seems much easier. So
I vote remove 2.
I vote remove 2 as well.
Okay, which pile do you want to remove?
Let's remove the left.
The left one.
You can't do that. Make another move.
Okay, let's remove the
whole right pile.
All right, right pile is gone. I would like to
Your
remove
turn.
the whole pile.
I would like to reject that move.
All right, I'll take a token.
Sweet. Oh wait, so
we only have one move,
still take
so they
this.
can't reject it,
right?
Because it's
yeah.
Then they would be
you used your one rejection for the turn. I made my move. Now it's your turn.
Yep, we'll take the one move.
Yeah, we'll remove the one disc.
Good game.
Again.
Woo!
Well done, all of
And
you.
in particular, you couldn't reject us removing the one disc because that would have left us with no available moves.
Correct.
Right. Cool. Okay. Sweet. That makes sense. Thank you.
All right. So now that that is done, let me switch back to my presentation. So how can we arrive at strategies like the one you guys just made in general? So under standard combinatorial game theory, zero rejecting, we can say, strategies go like this. The game is losing if the empty game, if you're in the empty position and you're under normal play, or there are no moves to another losing position. There are no draws, so either you are forced to lose or you can make your opponent lose. And if neither of these conditions are met, you're winning. Under K rejection, things are not the same, but they are a lot similar. The game is losing if no moves remain, and you're under normal play. Or there are K or fewer moves to other losing positions and a move to a winning position. The reason I have this second part here is if you don't have a move to a winning position, I can't reject all of your moves. Either I will run out of rejections before you run out of losing moves, or you will have a last move that I can't reject. So if you have K or fewer moves to losing positions, enough moves that I can reject, and you have a winning, and you have a move to a winning position that I can force you to give me, then you're losing. Otherwise, you're winning. So let's see what that looks like. This is the game that I came across online that's sort of, it piqued my interest, and generalizing how it works led to this topic that I'm sharing today. It's a 3-round web game of one rejecting normal play nim.
What do you mean by 3-round?
Well,
It's like 3
it plays
consecutive
3 games. Yeah, 3 consecutive games that you have to play against the AI.
Okay.
So does
And the
that
challenge
mean
is
when moves run out in round 1, the next player starts round 2?
the challenge is to win in these 3 games in order.
Okay, win all 3.
Yeah.
Okay.
Okay.
So I stumbled across this just browsing games online, and that's what led to this whole field that we're just dipping our toes into today. So let's look at how to win this game. Here's a diagram I have of the P positions, the losing positions, for 2 heaps of one rejecting normal play nim, the game we just played. This W right here, this is the winning position that I just had you guys win against me. And we have this whole graph. And we can immediately see the difference that K rejection is applying, because in the 0 rejecting case, we would just have a straight diagonal line of losing positions and winning positions everywhere else. But now we have these 2 diagonal lines. And we can kind of see what the rules we were going over before being applied here. the empty game is losing because we're in normal play. These two positions are winning because the only move to the losing position can't be rejected. 2-0 and 0-2 are losing because the move to the losing position can be rejected. So this move to the winning position can be forced. 1-1 is losing because both of these moves are to winning positions. All the games down here are winning because you can either go to this line of losing positions or this line. And you can reject one of those plays, but not both. Similarly for this big rectangle in the middle here, big diagonal rectangle. And we see the problem here because we saw in the diagram that one heap of 2 is losing. 2 heaps are 2 of winning. You guys won that game with 2 heaps of 2. And that's a problem because in standard combinatorial game theory, everyone who was here for Dearb's last talk remembers losing positions are supposed to behave like 0. They're supposed to be games that don't change the outcome, because if you try to move in them to make them beneficial to you, your opponent can always undo that change and leave you back where you started. But this is a problem because now it means we have different kinds of losing positions at the very least, because some can combine to losing positions and other ones can't. And so I made this diagram. On the left, so the X and Y axes, the X axis is how many 1 heaps you have in a position. The Y axis is how many 2 heaps you have. And we're assuming that there are no other heaps in the position. So we're just looking at the slice of the game space consisting of 1 heaps and 2 heaps. On the left, we have 0 rejecting standard gameplay, and everything is additive. We have this nice lattice. Every position on here, its double is losing. But that's not the case on the right. We have this fringe pattern. Yeah, Sprague-Gundy violated. Big news, big alarm, everyone's sad. We have this fringe pattern that violates that addition principle, and yet at the same time as the game gets big, the lattice returns. It's shifted, but it's still there. I'm going to get into this in my last slide, but basically what's happening here is as the game gets very large, you have a lot of copies of every move you can make. And so since you have more copies of every move, then the opponent has rejections, sort of in the limit the game becomes normal. The rejections fade out, so to speak. Which is why only the outer edges, when there's 1 heap of a given size, it's only those situations where we get the rule-breaking values. Here I have diagrams for 2 and 3 rejecting NIM, 2 heaps. And actually, let me pull it up here.
Sorry, so these are heaps of size 2 on all of them?
No,
Oh no,
this
it's two heaps, right?
Yeah, 2 heaps in
Here's
2
4.
rejecting NIM and 2
Gotcha.
heaps in 3 rejecting NIM.
It looks like there's k+1 diagonal lines.
Does.
Yes, that is correct. I'm going to get into that a bit later, but essentially, to have a winning position, you have to have more moves to losing positions than your opponent can reject. So once you get 3 of these in a line, everything further along that line is winning,
Oh, okay.
at least for the lines that you can move along. I did
Hmm.
also analyze Wythoff's game. There are some very those diagrams are very interesting as well. I should have put them in here, but I didn't. Because like in the zero rejecting case, you have those golden ratio lines that were alluded to in the other talk. And when I looked at the one rejecting diagram, what you see is there is a magnified copy, or what appears to be one. I didn't manage to prove it, but it certainly looked like a magnified copy of those same lines, but offset like in the middle where you see this line beginning, and then it's all wrapped in this like oblique cone. But then when I started looking at two rejecting Wythoff's game, the golden bit just went away. And in both normal play and misere, you just get this double diagonal line like you see over here, except at
You
a
should
knight's move angle.
after the talk, you should post them in the chat, and I'll put them as like the thumbnail of the talk on YouTube.
Okay. Yeah, I do have that. I don't. I have it on. I have a picture of that on my phone.
Sweet, thanks.
Yeah, I will show that. But what I also want to show is I spent the morning graphing in GeoGebra all of the 3 heap losing positions, sorry, for one rejecting Nim. I'm going to...
Let's go.
Sorry, can you repeat that?
Oh, I
Let's
was just
go.
making excited noises. Let's go.
Yeah, let me see if I can bring up that file real quick.
So to
Open...
be clear, we're talking like a 3D grid.
Yeah, a 3D diagram of 3D scatter plot of losing positions.
Sweet.
Here it is.
I'm not sure if you're aware, but it seems like you're only sharing your slide viewer thing.
Yeah, I just brought it up, so now I'm going to switch over.
Cool.
Let's get out of there momentarily and into here. Okay. Now we're looking at it from the side.
Oh, sweet.
This is what we're looking at.
Whoa. And the different colors are like different kinds of winning, or sorry, I mean they're losing, but different kinds of losing or something?
I colored these sort of just by by which heap is the largest.
That doesn't have to
Okay.
be a Sierpinski triangle, is it?
You are...
There's...
Why are you spitting? You are exactly correct, as a matter of
It
fact.
does look a little... Oh my goodness. Wow.
Pick that up.
There is a Sierpinski triangle. There's 3 of them.
Searing the Pinsky.
And yet we're not doing the sort of bitwise XOR that you see in regular NIM, because these 3 sets are all along the planes where the biggest pile is 2 more than the sum of the other 2. That's what we're working with here. So we're not
Why is that a thing?
bitwise. I have no idea.
Okay, cool.
This is not something that I've managed to formally prove yet, but you can these edges, these are the big diagonal lines on that 2D slice we were looking at earlier, with just 2 heaps. So I guess the reason why everything is on that plane is because we're sort of bounded by those lines that pop up in the 2 heap game.
Hmm.
But in addition to these, we also have this sort of central spine. A lot of games on here that are all 3 the same. But then we also have these clusters sort of around it, located right around the powers of 2, as a matter of fact. There's a triangle
Whoa.
here corresponding to the 889 positions. We have the 445 positions over here. We have the 445. I don't know if I said 455 by mistake. We have the 322 position over here.
I
And
think
then
you said
there
it,
are
but I just missed it. What is the coloring?
Maybe that makes sense a bit. So these
Oh,
red
it's just
ones are the one where the
uh-huh.
X heap is the biggest. The green
I
ones
see.
are the one where the Y heap.
What about those other yeah, what about those?
Yeah, there are these other
It's like big but not quite as big.
well, they're very big. These I've only graphed the positions where all 3 heaps are less than 10. So I think those are more Sierpinskis that just extend way beyond the edge of the grid. I have a program that I think has a closed form solution for a 3 heap game, but I've never managed to prove it. I think that is at the end of my presentation. But we have all these different like classes of points. I'll just set that aside.
Neat. Thanks for sharing this.
Yeah.
Is this is there a combinatorial game theory literature on the K rejecting games?
I have no idea. Probably not, but
Where did this come to be? Was this like some Stack Overflow question that you got hooked on or something?
no, I got hooked on this after playing that game I was telling you about.
That web
Gotcha.
game.
And
Does
Yes,
that
the
still
web game.
exist?
Yeah,
That's just like one person's game. Who came up
Yeah.
with the term K rejecting game? Is that your term?
that
Or?
that is I came up with that.
Gotcha. Okay.
Oh, nice. Okay.
Yeah, this is my attempt at generalizing the behavior of that game to
Cool.
games that can be played similarly.
What
That's
if we
fun.
vary K
We
throughout
don't
the
know if there's
game?
like a generalized Sprague-Grundy for K rejecting games. Obviously, the theorem as stated is not true, but like
Right.
you might suppose there is still some analog where like there's some like Sprague-Grundy essentially says that like the nim heaps from 0 through n arbitrary are like the only relevant positions or something. And here obviously that's not true literally, but maybe there's like some other list of relevant positions that's longer.
Right. That may be possible.
I mean, I don't
At-
know, like, literally just off the top of my head, but it seems plausible.
Yeah, I mean, at present, I'm not nearly at the point where I could prove or disprove that. I'm still just kind of in the like gather all the data and see what looks interesting phase.
Oh, yeah.
Maybe 10 years down the line that might change. Who knows? But we're not there yet.
Akiva Weinberger asks in the chat, what if we vary K throughout the game?
Yeah, I saw that. The answer is I don't know.
That would be a question of how are you varying K throughout the game?
Yeah, because if you allow k to vary through the game, you're basically playing the game unless the way that k varies is decided before any moves are played. You're basically playing with infinite k. So any person is forced by his or her opponent to play the worst move. Which I guess that would be interesting, but that's
Wait,
not
sorry,
something I've looked
infinite
into
K?
yet
What do you
either.
mean by that? Why is it infinite K?
Well, not arbitrarily large.
Why is K?
If
But like, I
if
mean,
k is allowed to vary freely. I see
Yeah,
in the chat
if
it
it
says
can be
maybe it's
arbitrary, then I agree with you.
yeah.
I was thinking
But you
like
could also say, like,
we have some general function like where n is the turn number, or maybe as a function of the state of the game, k is some value. So like you have some f that takes in the state of the game and hands you back a k.
Yeah, if it was based on just the game state, then theoretically that leads to a game tree that you can analyze. I don't know how you would approach any other sort of problem.
Yeah.
Like definitively, I'm sure you could write a program that could heuristically analyze it like we do for other games, but I wouldn't know how to answer that definitively. All right. Let's get back to the presentation. There we are. I also looked at Fibonacci nim. Just an example of how this might affect other slightly more complicated games. As a refresher, it's a game played with a single heap of tokens, where the first move isn't allowed to end the game immediately, and then after the first move sets the stage, each subsequent move can't take more than double the number of tokens that the previous move took. And why this is called Fibonacci nim is because in the standard case, Fibonacci numbers are the losing position. So I wrote a script in parallel to the one that gave me all these positions for nim, just to sort of see what would happen if I programmed in a routine for Fibonacci nim. In the one rejecting game, the losing positions are the Fibonacci numbers, only up to 8.
Not 8 factorial.
Not
Okay. I wasn't sure.
Not 8 factorial, sure.
So, yeah, I'm running the script.
30,320.
13 doesn't show up. 21 doesn't show up.
Can you explain why 2 is not a losing position and 0 rejecting? Don't you have to take 1? And then your opponent
maybe
takes the remaining one?
Yeah, and then you lose, right?
No, maybe I was wrong to put that.
Wait, but
Oh, crap.
if you take 1, then your opponent takes 1, and then you lose. So 2 is losing.
Yeah,
Right?
I
Oh yeah,
didn't have
this says losing.
initially I
position.
didn't have it set that. Then I have it. Maybe I misread my code output or something. Oh goodness. Hang on. There we go. Right. I think I put in something wrong about 2 here, but
Okay.
nice disclaimer in the chat. Yeah, but point is, Fibonacci numbers stop being special after you hit 8. 8 behaves normally. 13 doesn't. 21 doesn't. 34 doesn't. I managed to run it all the way up to confirm that 987 is still winning instead of losing like it should be. I don't know about higher numbers, but I suspect the pattern continues.
And then all the non-Fibonacci numbers are still winning?
They are still winning.
Okay.
So you hit 8 and everything above that is winning for player 1, you're saying?
As far as I can tell.
Huh.
I tested up to 1,000.
Well, I
After
guess,
that, it
was
got
there
a
a general strategy here where you're just like, I mean, if all of the losing moves are sufficiently low, then I think the one rejecting strategy would just be to, like, before 8, there's at least 2 Fibonacci numbers, so you just take the whole heap except for like that remaining low Fibonacci number, and if your opponent rejects, then you just take the heap for the slightly low Fibonacci number. How many Fibonacci numbers
Well-
are there before 8? Like,
1, 2, 3,
why is
5.
it 8?
I don't know.
Oh.
I didn't actually look at the game tree. Remember, there's this restriction that carries throughout the game
Right.
that you also have to keep track of. So I didn't look at the full game tree.
Right, but if you're taking this sufficiently large amount of pieces on the first move that it's
Yeah, I
more than a
suppose.
half of the heap anyway, then it doesn't even matter. Like, it's the same as the first player being able to take the whole heap, or not being able to take the whole heap, but like,
Right,
able
I
to
see
take
where
as
you're
many
coming
as they
from.
want.
That
I
might be
think-
it. That might be it.
Yeah.
Great. These are like the sort of discussions I wanted to have across this anyway. Maybe some of you had insights. Yeah, I might look into that.
I'm curious why it's 8 though. Like, I would imagine as soon as you hit 2 Fibonacci numbers, like, to be clear, when you're saying up to 8, you're saying 8 is
8 behaves as you would expect.
as in 8 is losing.
Correct. It's a losing initial position.
Right. So I would imagine, like, I would have thought it would be like 1, 2. I don't know. For the really low cases, it's hard to think through
Yeah.
in my head. But like, I would think as soon as you have a smaller than 5 amount of low Fibonacci numbers, that would be enough for the player 1 to just,
Yeah,
like,
because
say we have 8.
Yeah.
Let's just try for the case of 8. Because I'm
Wait, why
curious
is
now.
3? Why is 3 losing? 3 is a Fibonacci number, right? And
Yeah.
then at 3, I say, okay, I'll take away 2. Wait, sorry. 1 is a winning position. Oh, so I'm. Never mind.
Yeah, if you
Wait, 1
said
is a Wait, 1 is a winning
One is
position?
because
Should this be saying
yeah, you make the last
Fibonacci
move.
numbers? Well, but 1 is a Fibonacci number.
So there's another rule that wasn't mentioned, which is that the first move can't take the whole pile. So if the game is starting with 1, it's a losing position because you can't make the move. But if
Right,
it
the
gets
game's
down to
starting with
1,
one
then
is
you could take
losing.
it.
yeah, this is
So
actually
you have to
there's like
pass.
there's like 1 parentheses start of game and there's like 1 parentheses not start of game or something.
Does
Right.
this
This
change
game
the
has
way
like
that
an
things are
extra piece of state, right?
the sum of
Which is
games?
whether it's
Yeah.
the very first turn or not.
Yeah, that makes sense to me.
I did not look at sums of this game. I have the capability to. I did put that functionality in my program.
I'm just wondering, how would the start condition affect the sum? Like, does it carry forward if you sum 2 games and one of them begins? Are you now allowed to take the whole pile from the second?
The way I have it implemented, and when I was like looking up on Wikipedia how this game is supposed to be defined, I think the rule is you can't take the entirety of the largest pile. At least that's what I have implemented.
Okay.
But I
Whoa.
didn't analyze multi-heap games
Wait, but
when
you
I was
can
gathering data for this.
you
Yeah.
can later,
I
right? It's
suppose you
still only
could.
the first move
Yeah.
that you
Yeah,
can't
I
take
have
the whole
some
move.
Moves
comments
after
about-
the first are only determined by the move that just happened. So we only have an edge case for when there is no move that just happened.
I think I can clarify a lot of the questions about sums of games that came up at the beginning and now, but I think it would distract. Like, I want Axiomatic System to finish the main stuff before I go on that tangent.
Yeah, that would be great.
So wait, I have another question. I'm very surprised about this result about Fibonacci numbers excluding 2, because like once again on move 1, couldn't we just take the whole pile? Uh, Never mind. No, I think I answered my own question. I was going to say, couldn't we just take the whole pile down to like a low Fibonacci number, and then but then the other player could just take the whole stack. So you're encouraged to take a small thing to start.
Right.
But
That's the
wait, so
general.
yeah, mhm.
That's the general idea behind the zero rejecting strategy, at the very least.
Right. So I want to try working through like a small case of like k equals like 5 or 8 or 3 or something like that for the one rejecting case. Like let's say we start at 5. Then we remove 2 to get to 3, which is in theory a losing position for the opponent. They would reject that. Then we go down to 2, but that is then winning. Right, yeah, I think the quirk here is as Planet was saying, like there's a difference between the starting case and the later, like the case where the board has been developed and now you can take the whole heap. That seems to explain the strangeness in behavior with the exclusion of.
Yeah. Like in Nim, we're used to the whole state of the game being the number of things in the pile, but in here there's actually 3 states. There's
Yeah.
is it the first turn, there's what is the
Right.
maximum number of chips you can take on the next move, and then there's how many chips are left.
Yeah.
So you have to track all 3 of
Well-
those in your game tree.
2 variables, because you can reflect whether it's the first turn or not by just an appropriate default value of how many chips you can take.
Yeah.
Can
You
you
can
though?
store both
Because
of those
like
points.
because first turn you can take up to n-1. Oh, it's
Yeah.
double previous move. It's not double max of previous moves. Oh man. Yeah, okay. I'm sold. I'm sold. I really someone else asked a question that was answered on the slide, and I'm really like, now it's my turn. I got to ask a question that's also answered on the slide.
All right. Well, I'm glad I could clear that up for you. All right. Yeah, we can discuss more of that later. So the first thing I came up with, sort of as an answer to how can we evaluate these games, determine whether games are like other games, I came up with this concept of a signature. And what motivated this idea was, again, how we look at zero rejecting games. We see that nim values are a way to reduce, via Sprague-Grundy, a way to reduce combinations of games into individual games. And the entire point of that theorem is to say that this sum of games is equivalent to a single game. And so the thought I had was, well, in zero rejecting games, you can carry out strategy stealing, which means that zero rejecting games are self-canceling. If you have 2 copies of a game, under normal play, if you play one, I can mirror your move in the other and force you to have the last move. So I combined this with what nim values are supposed to do, and I thought, well, maybe I can identify games by Sedenians like the 16-dimensional non-associative algebra by virtue of being a version of an already established field of numbers, but without all the properties that make them easy to work with. Yes, I did choose that term deliberately. To answer chat. So I came up with this idea of a signature, which is the collection of game states that cancel the position you're currently looking at. So a signature for a k-rejecting game, it has to have more than k entries by the principle that I showed you on that other diagram, because if there's only k of them, then for a sufficiently large game, there always have to be more than k losing moves available, irrespective of any other positions. Like if we go back to here, and we just look like down this column, say, if we go arbitrarily far down here, every game down here has to have 3 losing positions to see somewhere. And they can't all be off to the left because there's only finitely many games over here. And each of them, inductively, only has finitely many losing positions in their signature. So as I travel along this new row, I have to have these 3, or 2 if k is 1, or 4 if k is 3. I have to have these games in the signature no matter how far down these I go. So I can say with a fair amount of confidence that a signature is going to have more than k entries, and that a nim signature, k rejecting nim, it's always going to have k plus 1.
I'm confused about, like, it seems like you're talking about moves, positions that you can move to.
Yes.
How is that related to positions that you can add?
Well, I make this analysis of the positions I move to as I range over all the positions I can add. So when I was scrolling down that 4 heap column, I can say that the signature of 4 had to have 3 entries in it.
Can we see an example? Can we see what the signature is of a small case?
Yeah, sure. That is going to be on my next slide here. Example
Great.
signatures.
Okay.
For one rejecting nim. The empty game and the game with 2 1 heaps both have the signature 0-2. So these games are both losing if I add the empty game to them, and they're both losing if I add a 2 heap to them.
Is a signature unique? Sorry, could you go back to the definition real fast? Like, are we talking about the minimum set, or sorry, the minimum number of positions?
No, I think
No, these are the only 2 single heaps that can be added to these 2 games to turn them into a losing position.
So a
Single
signature is
heaps.
a
We're adding
single heap.
A signature is a collection of single heaps, yes.
so. Yeah, I think
Okay.
the thing that was missing on the previous slide. So if you go to the previous slide where signature was defined, it just says position that you can add to get a P position or something like
Yes.
that. And I think
Maybe
you
that
mean
was a little vague.
single heap nim, like single heap nim under the same rejection rule or whatever.
I did leave that vague because it is, in theory, it's a scheme you can apply to any of these games.
But like
So
the signature having size 2, like if I believe the slide in front of me, then certainly the only single heap nim things you can add to 1-1 are 0 and 2. But like maybe there's like a game of chess or like impartial chess that you can add that's totally different. Like I don't know.
Of course, that
like
is
that would
one of the
change.
shortcomings that I ran into while trying to develop this.
I'm
That-
confused about the notation here. You said we're adding single heaps. Are we saying that that parenthetical expression here is two single heaps that when simultaneously added to our game of 0, thus making it 0, 0, 2? Or are we saying that either the option 0 or the option 2 can be added to the game to make it a losing position?
It's the latter. Either one of those two can be added to the position.
Okay.
Yeah,
Yeah,
so
So
I
you have-
apologize. It
like
is a
that
slight
braces.
abusive notation, but
And you have not or we are not yet considering, for the sake of this talk, what happens if we want to add multiple stacks, multiple heaps simultaneously to the existing game. That's not what we're talking about in this slide.
no, because this was my attempt at consolidating effects of multiple games into single games. It didn't work.
Okay.
But this is just something I've tried that
Yeah,
produced
just trying to make
interesting.
sure I'm following the actual claim on the page.
Yeah, it had interesting properties in its own right. It's what helped me define the formula that I believe solves the 3-heap game, but as a like grand overarching theory of these games, it falls very far short.
Okay, sorry for sidetracking.
That's fine. So, as an example of how this fails, the position 3 heaps of size 5 has the same signature. But if we add 0 or 1, 1, if we add either of those positions to 2, 4, we get a losing position. But if we add 5, 5, 5 to 2, 4, that's a winning position. So clearly, signatures are not going to be enough to help us classify games.
Wait,
Just-
I'm lost again. We're saying now adding 5, 5, 5 as a single set of 3 heaps. Previously, the parentheses were used to say one of the two. Is that right?
Yeah. Adding 0 or 2 to any of those 3 games results in a losing position.
The thing that's
But those
confusing,
3
I think,
games can't be
here-
equivalent because they have different effects on other games. Does that make sense?
Mm-hmm.
Yeah,
So
the thing that's confusing here is that the parentheses with commas are being used for two things in different places. On the right side of, someone's saying this in the chat also, but on the right side of the colon, they're being used for like set notation or something like 0, the set containing both 0 and 2. But on the left side of the colon, for example, 1, 1 and 5, 5, 5, they're being used for like nim heap notation.
Correct.
I think
Yes, that
is what
was a
answers.
poor choice on my part. I apologize for confusion that has caused. But yes, that is how you are supposed to read this.
So the point that you're trying to make here is that. Say that again. Say the last thing you just said.
Regarding
Like-
the slide?
Yeah, like no, but not regarding like what was your actual point? I'm so stuck on notation here that I'm trying to figure out what you're actually trying to say.
Okay. From the top.
Yeah.
The 3 games, the empty game, the game with 2 heaps of size 1,
Mhm.
and the game with 3 heaps of size 5.
Yep.
All 3 of those games have signature 0, 2.
Yeah.
So they're losing by themselves, and they are all losing when a heap of size 2 is added to any one of them.
Yep.
But these 3 games are not equivalent because they have different effects when added to other games such as 2-4 in the example there.
Okay, yeah, so it doesn't form an equivalence class under combination, is what we're saying.
Correct.
Okay.
Naturally, this kind of bummed me out. But the other day, partially inspired by the talks on combinatorial game theory, I came up with the idea of extended options. So, as everyone who was there for his talk saw, we have this notation for normal games where we have these two sets of options, available final positions for each player, and we can write them like this. Now, we could just do this directly and build up inductively like isomorphisms between game trees. The problem is we don't have access to any of the usual tools regarding, say, dominating strategies or reversible moves, because the ability to reject moves makes the analysis of those a lot more complicated. But there is sort of a property of all these games that I've alluded to before, which is if all of your moves have large enough multiplicity that they can't be rejected, then in the limit we sort of approach this normal game structure. So what I've arrived at is not this elegant, of course, but we have this. We sort the moves available to each player into all of these buckets. Okay, I see your chat message. Nice. And these subscripts denote how many moves are available to each of these positions. Now, this has to be built up inductively because we don't want any surprises where, say, there's a position here in R1 and a position here in R2, but these games are secretly the same, so really they should both be unified in R3. But sort of the claim that motivates this structure is that we can use this structure to analyze these games just like how zero rejecting games are analyzed with this two-set syntax. And this extended structure directly contains this smaller structure, because if we have a game that's inductively built up where at all stages all the moves are either in this bin or this bin, well, those are all the moves that can't be rejected no matter what. So that's just going to be isomorphic to a zero rejection game, no matter what K actually is. And similarly, even if K is 2 or 3 or 5 or 10, if every step of the game tree only has moves in these two bins, you can play that like a one rejecting game. At least I think. I'm pretty sure that's true. But we have this kind of nested structure that lets us talk about all of them. And sort of the key point of that is that the one tool we do have available to reduce the game tree is the fact that we can group all the unrejectable moves together into these two buckets instead of forcing ourselves to only deal with game trees that are fully isomorphic. And that's kind of as far as I've managed to develop it at the present time.
Thank you. This is given a lot of things to think about. I know we
Yeah,
don't
that's
have
pretty cool.
It's pretty strange. So we'll go back to this scene, and I will now open the floor to anything that's struck you guys as something worth discussing. Or we can play
one-
that 3-2-1 game.
One random question off the top of my head for Dirib. He mentioned at the beginning in the chat that he thinks it will be about game theory and not CGT. Just want to confirm that my mental model of what CGT is correct. This was about CGT, right?
Yeah, no, I was going from like the words in the description just said game theory, and I remembered that, and I just assumed it was non-combinatorial. And since I didn't know what K rejecting was, I figured, oh, that must be some traditional game theory term I don't know that's like established in the regular game theory literature. Was my guesses there.
It does really sound like a regular game theory term to me.
Yeah. Like you're playing the prisoner's dilemma and you reject the cooperation K times and then or something, That's not what it is. I know we don't have too much longer for recording. I did want to try and clarify a bit about sums and such.
Sure.
So the sums that we've been talking about in all of the talks on combinatorial game theory so far are all one particular type of sum called the disjunctive sum.
Yes.
And so, like, the sum is totally set as the point was being made at the beginning. The type of combination we're using is totally separate from like how we're playing the game. And so, keeping it too impartial, you just have a bunch of components with a bunch of sets of moves. The disjunctive sum is the thing where there's finally many, and they all have to be over, and when they're all over, then the game is over, and whatever the rules of play say about how that works is how that works. And the disjunctive sum has this natural interpretation in this K-rejecting setting, where you propose a move on one of the components, and then the opponent can reject up to K times as long as you have some other move to make, etc. But like a different combination would be, oh, it ends when the first one ends, or you choose some finite bunch to move in instead of just one of them, or whatever. There are lots of variations, but this one is this one. And then the other thing I wanted to say,
could have made that a bit more clear.
What is the name of the other sum where like as soon as you win any game you are the winner?
I would have to. Because with just the vague stuff I said, there's like 12 different possibilities. I don't remember the names of which ones are which off the top of my head.
Gotcha.
Okay. Like conjunctive sum is one of them. Short disjunctive or long disjunctive, one of those is different than regular disjunctive. There's a billion names. I'll look it up later.
Okay, thanks.
The other thing I wanted to say, what were we talking about? We were talking about the strategy. Oh, for Fibonacci, we were talking about adding copies of Fibonacci nim. And so, because disjunctive sum means what it means, period, full stop, and the discussion we had about the states of Fibonacci nim, I like the comment in the chat of Akiva Weinberger of basically the starting state of Fibonacci nim has like a heap of n and a pretend amount that the 0th move took, and that's a pair for the state, and that is the state of a component, and so that can't take the whole heap rule that comes from just the state of the pretend 0th move. That could be in 5 different components. That's fine. It's not like you have to say, oh, the very first move of the game has to be such and such. if you say something like that, you're automatically not talking about the disjunctive sum anymore, because you're imposing a rule as to how we play the components that is artificial.
Right. Okay. That's
But like
understandable.
it could be generalized if we do actually incorporate that into the state of the individual game, correct?
I'm not
The-
sure what you mean.
I think the
like if
point
we
is that you would have to call the combination, the resulting combination would not be a disjunctive sum, I think is the point he's trying to make.
Well, yeah, and I'm
Or
suggesting
something like
like, you
that.
know, if we go ahead and like say instead like we're only talking about the amount of pieces that either player could take on that particular game as a function of the amount of um, pieces that were taken off of that particular heap on the last turn, then we can combine that number into the state of that one particular heap itself, and the disjunctive sum still works.
I think I'm saying the opposite of what you just said, but I'm not sure.
So like,
Disjunctive
I'll
sum says each component game follows its own like rules for what moves are available separately, period. They do not interact in any way, shape, or form.
Yep.
And so if you're talking
Yeah.
about combining things into one heap, or the biggest, or the number that was taken on the previous term from any heap, then you're not talking about
I'm
the
not talking
disjunctive
about
sum anymore.
I'm not talking about any's. I'm saying like, you know, if we make the state of each heap be the size of the heap, comma the amount that was taken on the last turn, then you could put those in disjunctive sum, and each heap individually would have its own condition on how many
Yes, exactly.
moves and that's still a fine disjunctive sum.
And Planet points out we could certainly play a different game. We could call it like multi-heap Fibonacci nim or something, where there's a global remembering
Right.
of what the previous thing was. But that's a different.
And that is
That's not a
no
disjunctive sum, but
disjunctive
it's an
sum.
interesting game.
Yeah. I'm with you.
So yeah, those are basically what I had to say about sums in terms of like ideas and ways to think about tackling K-rejecting games. I want to give like the next 10 hours of my CGT lectures, and then we would be in a good position to make analogies and like attack this it from a really like good. We would have a lot of good ideas as to how to attack this, I think.
Yeah, I would definitely agree with that. Does anyone else have anything?
Well, just to end it, anybody want to play this 5 heap nim game?
Oh, just the 3. I won't be that mean.
Just the 3, meaning the 3 comma 2 comma 1?
Yes.
The 3 heaps?
Yes.
Okay.
If you want me to bring up the slides again, the strategy was
no spoils, no spoils.
Okay. Okay.
And does anyone want to play with me? I feel like Axiomatic System already knows the answer here, so it would be more fun to play with someone random.
I'll give it a try.
Sweet. You want to go first or second? I haven't thought it out yet.
Second.
All right. Give me a moment. You know what? I'm not going to even bother trying to
Wait,
recursively
what are
think
we
through this
using
right
one
now.
rejecting?
Yes, this will be a 1 rejecting game.
Okay.
All right. I'm just going to request to remove a Dude, hold on. One thing that I don't like about this position is that it's hard for me not to make something that is like a mirrored position. Like you're always going to have 2 options going forward, I think. For most things that I do. I'll delete the 2 in the middle. That'll be my first request.
I will reject that.
Okay. I'll delete 2 from the left pile.
All right. That's the move.
Okay.
K is 1.
Correct.
Answer the chat.
I will delete the 2 in the middle.
I think I should reject that, but hold on. um, yeah, I'll reject that.
I'll delete 1 from the middle.
Okay, I guess I'll delete 1 from the left.
I reject that.
I'll delete 1 from the center then.
Okay. I'll delete the right.
Go for it.
Okay.
And I'll delete the left. Yippee!
The game.
Well done.
Thank you. Good game. Cool. Any other questions?
What was the? I'm curious. What is that
Correct,
a
Akiva.
winning
You cannot
position?
reject the last remaining move. Sorry, what?
Was that a
Was our
winning?
play optimal? I think was the
Or
question.
did I play? Yeah.
Yes. First move was actually correct.
Sweet.
I think.
Okay.
Yeah.
Wow. I'm surprised.
And then everything else looks pretty good.
All right.
I
My
did
last
my
comment.
best.
I guess it was optimal with the exception of Gray Cuber choosing to go second.
That is
Yeah.
true.
So at the end, it sounded like you were saying that if we have more than K copies of a move, it doesn't matter how many copies we have. I don't know if I believe you.
If that move is the move you want to play, and you can threaten it more than K times, I cannot reject every one of those K plus something
I agree with
threats.
that.
Yes.
Yeah, that's true.
But if you want to play a different move, you can just trash a bunch of that unwanted move. Oh, they could allow
No, but
it.
they just permit you to take the bad move.
But what I'm thinking of is like, okay, you have like we're playing one rejecting, and there's 3 copies of some move I want to make. You can't stop me. I make it. Now there's only 2 copies of that move if it ever becomes relevant later. Does that matter?
I think we're only
No,
talking
because
about
you're in
the
a different
present
position.
scenario.
Okay.
Now you're in a
Okay,
different
got it.
position with a different set of moves.
I think it's just a local claim about like, if at a given position there's a move that you want to play and you have K copies of it or K plus 1 copies of it, then you can force that you can make it. I don't think it's a deeper claim about the persistence of that option throughout the game.
But like if this notation is going to be all the notation we need to keep track of for the game, we need to know about the whole game.
Yes. I was not making a claim to the contrary.
Yeah, I'm contradicting 2Swap, not you.
Oh, sorry. Wait. Could you say that again? I failed to see the contradiction.
No, so it sounded like you were saying, "Oh, we're just making a local claim about things right now," and I was saying, "No, if Axiomatic System is saying this notation captures what we need for the whole game, we're not just making a local claim."
When I say local claim, I mean a local claim about the outcome of the current position, as opposed to the outcomes of positions in the future regarding.
Right.
Yeah.
Yeah. No, I understood, and I disagree that that's what Axiomatic System was saying.
Please repeat your.
Should I bring up that slide again just so we can?
That would be great.
All right, give me a second.
You could also just tell us which of us is right.
Well, I'm not even seeing the point of like what is your specific claim, like as opposed to saying what you think that I said that was wrong. What is your exact statement?
That the
Like could
intent of
Mhm.
notation, that axiomatic system's intent, which I'm guessing at, and he could just tell me whether or not I'm right, for the notation that keeps track of how many copies of moves we have, except it doesn't keep track of things past K, is to have a notation that carries enough information about the game state to tell you, like, all things about all outcomes down the road, and in sums. And
That is
I'm either
correct,
right or wrong
because the
about it.
point of that notation
Oh.
is to every level of the game tree can be represented independently and inductively with that notation. And if you use it to match up, if you use the buckets in the notation, I'm trying to get to that slide. But as long as everything is correctly grouped, then games that are notated identically should be isomorphic, or well, should have the same strategy.
Yeah, I think actually I take back my very original thing, and I do believe you.
Should we be able to see your slide?
I
Yeah, we can't see anything.
just got there. I was having trouble
Gotcha.
bringing it up. Give me a second.
No worries, no worries.
Here we are. So, are there still unresolved questions as to what this all means before I go over it again?
I'm good.
All right.
I'm just thinking. But I can do that on my own time. I will ponder this.
All right. Yeah, I can definitely like share this in chat afterward at some point if people want to look at it on their own time.
Well,
All right. Well, thank you all for coming.
thank you very much.
Yeah, thank you.
I will see you guys later.
All right.
All right.
Bye bye.
Bye.
Bye-bye.